gentlemen, thank you for coming to this talk. Let me begin by telling you a little bit about the research in NTU. And by the way, my name is Lee Sui. I'm the director of the Institute of Advanced Studies. I also founded this school here, School of Physical and Mathematical Sciences. Now, NTU has progressed tremendously in research, especially in the last 10 years. In 2007, if you look into the Web of Science, NTU published about 3,700 publications in that year. Today, it has almost doubled to about 7,050. Now, our good neighbor down the road, NUS, publishes about 8,500 per year. But NUS is a much larger university compared to NTU. So I would say NTU has done extremely well. And it is not a surprise that NTU has risen very rapidly in the league tables. Okay? It's not a surprise. Because of the rise in the amount of research publications, especially in science. And of course, science is not contributed by science alone, also engineering. A large number of the science publications come from the College of Engineering, which we should not forget. Okay? Now, the IAS, because of this large number of publications, you would, any rational thinking would say that, you know, we have quite a large number of good scientists, including engineering scientists in NTU. So that's why we are going to start this series of groundbreaking science lectures. We are going to do one every month. Largely to introduce the so-called well-known researchers from NTU, which we don't sort of glamorize them enough, you know. But they're actually doing very well on the international scale. And also to introduce the kind of groundbreaking science that is happening in NTU. There's a lot of it. And if you look at the Shanghai rankings for 2017, you know, NTU is #1 in the world in nanoscience and nanotechnology. It is not surprising if you go and look into the Web of Science and then you look at the highly cited papers. Many of them are in the area of nanoscience and nanotechnology. NTU also ranks #12 in the, #5 in the world in chemistry. It's not surprising because material science and engineering, chemistry, biological sciences, you know, these people are also producing papers in chemistry, very good quality papers, including those that are coming from Professor Loh Teck Peng's lab. So let me say a little bit about Professor Loh Teck Peng. He comes from a little town, Peng, you know, which is about 100 kilometers north of Singapore. It takes about 2 hours to get there. So he had his education, school education in Peng, and then after he completed his high school, he got a scholarship to go to Japan. And he studied in Japan. He completed his bachelor's and master's degree, lastly in chemistry, at Tokyo Institute of Technology. So after he completed his basically an undergraduate education, he got a scholarship to go to Harvard University, Department of Chemistry. And then in 1989, that was the year I think that he went to Harvard. And then after doing his graduate coursework, he chose to work with E.J. Corey. E.J. Corey is of course a giant in organic synthesis. 1989 he was there. 1990, E.J. Corey won the Nobel Prize for chemical synthesis. So he spent about 5 years in Harvard. And then in 1994, after he completed his PhD, he came back to this region Fortunately, he didn't go to University of Malaya. He joined the National University of Singapore, I think in 1994, without doing postdoctoral work. Usually, today's academic path is that if you want to become a professor in the university, you have to complete your PhD, and then you spend 2 to 4 years as a postdoctoral fellow to show that you can do independent, good research before the university would hire you. So NUS took the risk, and took him fresh as a PhD. But for a very good reason. If you work with E.J. Corey, you have to work day and night. 5 years is like 10 years in NTU or in NUS. I am afraid that our students here don't work quite as hard. Because on Saturday and Sunday, when I come back to the lab, sometimes on Sunday, but usually I work 6 days a week. It's not heavily populated, especially in the evening. If you look at the top universities, the graduate students there are all working extremely hard. So I think that culture probably will have to improve in NTU. Well, NUS is the same, but that's not learned from NUS. So when he joined the chemistry department in 1994, at that time I was Vice Dean of Science. I remember that the head of department, in order to attract him to come to Singapore, we had to buy a 400 megahertz NMR. I think that was the first 400 megahertz NMR in NUS. Then today, of course, we have 300, 400, and 500. I think NUS has got 1 300, 2 400, 2 500. 800. They are 800. So in NTU, in the chemistry department, if you go there, you will also see a suite of NMR. We also have 300, 400, 500, and the 800 is sitting in School of Biological Sciences. It's like a national facility. All right? So without NMR, there's no point in recruiting Loh Teck Peng. Minimum 400 megahertz. Right? At that time, I think NUS chemistry only had a 300. Not good enough. You cannot publish good papers that way. So in 1994 to 2005, he was at NUS, and then in 2005, he took a big risk. He came with me to NTU, and I started up this School of Physical and Mathematical Sciences. A very big risk. But fortunately, since he joined NTU, his output of research papers proportionally is about the same as that in NUS chemistry. So today he has published about 265 publications. His H index is 56, which places him among the top synthetic organic chemists in Asia Pacific. In 2017, he won the Yoshida Prize, awarded by the International Organic Chemistry Foundation. And then this year, he won the President Science Award, which is the highest science award in Singapore. Right? And then the next prize he will have to aim is the Nobel Prize. Okay, so today, this afternoon, Professor Loh is going to share with us research in green chemistry, water as an agent of change, reaction media, and a super catalyst. Okay.
Thank you, Swing, for a very kind introduction. Nice. First, actually, I usually don't use research seminar in NTU, very rarely. And this is one of the very few research seminars I've given here. I think for the past few years, I've decided not to give research seminar. Like with the invitation from Swing, it's very difficult to decline. It's like coming to NTU. So in 2005, I followed him to come here. So I was the first head of the chemistry department here at CBC. Swing was the leader. So he brought a group of mafia from NUS. We have a physics head, NUS, Next we have Red Ling Sang as the provost, and then Alfred right now is the director of institute right now with materials. He started. So I still stay here as a professor. So I'm doing research. So still not working much, doing much on administrative work. So today I'm going to talk to you some research work that we have been doing for the past 20 years since I joined NUS in 1994. So what do we do as an organic chemist? Okay, so as organic chemists, we make molecules. Hopefully the molecules can be useful. A lot of times we focus on drugs, pharmaceuticals, designing new molecules that hopefully they are bioactive and finally become drugs. So you can see that, for example, this molecule here, Taxol, we try to make it. It's a very complex molecule, isolated from plants and other type of medicines, even bioimaging materials, agrochemicals, they are mainly organic compounds. Also, you talk about materials, for example, you talk about this material here, which is bulletproof materials, polymers, again, they are organic compounds. Right now, we talk about flexible electronics, again, they are organic compounds. And this is the compound that I worked on for a while in the US, try to design a new compound to make photochromic sunglasses. They can change color, okay? So it come in, I think right now it's in the market a lot. So in the 1990s, we're trying to find a new one, but unfortunately, we're not able to get a better one than the one in the market. So when I first came back to this region, to NUS, the first thing I asked myself is that what type of research I want to do in Singapore. So I look around and look at the Nobel Prize, and it's very ambitious, okay? And you talk about 1984 in Singapore, as Swing said, at that time nobody would apply. I only have one film cover, there's a wooden film cover. I think Chung Hong was one of my first students there, Prof Tan, who's right down the dean. Okay. So basically, I was ambitious. I thought maybe we can do something. And it's good because in Singapore, when you do research at that time, nobody take notice. Okay? No, until when somebody take notice, they realize it's dangerous. That means you are doing okay. Okay? So I look at the Nobel Prize and see what is done. And one thing I wanted to do is to find out reactions that I can beat any Nobel Prize winning reaction. Very ambitious, okay? So any reactions that you can beat Nobel Prize winning reactions, it should be a good reaction. Okay? So I look around here, you see that a lot of times we're focusing a lot on the way, trying to find a good way to make complex molecules in the 1960s. So there was no good rational strategy until Corey, Sui mentioned, that was my supervisor at Harvard. He came up with this concept called electrosynthetic analysis, thinking backward. And after he came up with this concept, any molecules they can draw on the paper, in principle, you can make it. So right now, all the drug companies, basically, they have to use electrosynthetic analysis when they design, when they try to make molecules, the steps, okay? So he also started using computer in coming up with strategy to make molecules. So he's the first one to do really, what they call it, applied computational chemistry. So he had a group of 30 when I was there, just doing computer. Okay? Every day they try to come up with programs, come up with ways to come up with good strategy to make molecules. But now these things are right now getting very hot. Now we talk about artificial intelligence, they're going to use for organic synthesis. So you look at many other Nobel Prize winners, they are focusing mainly on trying to come up with new and practical methods, just in terms of cost. Basically, they're focusing on cost. Cheap methods to do scale-up synthesis of drug molecules. So this was actually mainly the focus of many groups. But they want something missing here is that a lot of people are not mainly focusing on green chemistry. That means they don't bother much about environmental impact. A lot of times they're focusing mainly on cost. So in the 1990s, a lot of groups started to look into environmental impact, green chemistry, because of the environmental concern, okay? So you look at here, this is Corey. So I like the way Corey do research that. You come up with a strategy, idea to change the whole area of organic chemistry. Whole area, not just one simple thing, okay? The whole thing, and then you make it better. You cannot just change it and then you make it worse, okay? So you come up with this thinking, saying that look at the molecules like a shirt, see? You look at the color, they are all similar, the way to make it. You only look at the shape just changed, okay? So same thing, Corey was able to identify the patterns in the molecules. And these patterns looks different, but it's the same way to construct it. So from there, we start to cut it backward, think backward, and then reconstruct the molecules again, demonstrating that we can use electrosynthetic analysis. And this is only just one strategy. Another strategy that people use a lot is from the biological system, inspired by our body. Look at the way enzymes construct molecules. And if you look at the way enzymes construct molecules, they do it in a very fantastic manner, very efficient. And can you come up with a method that beat enzyme as a catalyst to do complex molecule synthesis? And this is another way to get the ideas, okay? So people come up with a different strategy and try to beat the way the biological system do the reactions. So you can see that usually chemists have a bad reputation. You say, oh, air pollution, chemistry. Water pollution, chemistry, okay? And then fire explosion, chemistry. So it's always bad reputations, okay? I think for many years we've been focusing just on profit cost, very rarely on the environmental impact. And this is extremely important. For example, you know the Minabata disease in Japan, it caused a lot of harm because of mercury, poisoning, explosions a lot, because we use a lot of chemicals that are extremely explosive. So I think we have to focus. So at that time, 94, I decided to look into maybe we should try to come up with methods that safe, green, and hopefully no waste, no toxic waste. So what we do as organic chemists, basically we design chemical entities, not just make it. We have to design, okay, chemical entities. And there's the power of organic chemistry. You can design molecules of your choice, okay? You want to make it color compound, you can design color compound. You want to make it flexible material, you can actually make it, okay? But you want to make it in the most efficient methods, effective in terms of cost. But now we wanted to add in another thing is that you want to make it in the environmental friendly manner. That means it has to be green. Hopefully no waste, no explosions, no fire, okay? So where do we get this inspiration? I think I always get the inspiration from nature, from the way our body makes molecules, okay? If you look at our body, we make a lot of complex molecules. We make steroids, biomolecules, and proteins in a very effective manner compared to us, okay, as the organic chemists. So these are some of the biological processes really that impressed me actually. For example, this enzyme here called aldolase, they're able to construct, to do CC bond formation reactions, to do aldol reaction in very efficient manners, and also able to control stereochemistry very efficiently. So in the old days, when we were students, we say that it's very difficult to beat these enzymes. But now, we have many small molecule catalysts that really can beat enzyme right now. Chumhong is also working in this area, okay? Organocatalysts. Okay, we have molecules right now that can beat right now catalysts. In the old days, the students would say you can't beat enzyme, very difficult, okay? Things change. And then there are many, you can see the way enzyme construct molecule. For example, these are complex steroids. Enzyme were able to construct it in a very efficient manner, very efficient. Also, these are reactions, very tough to do in organic chemistry, changing and nucleate into methanol. Okay, and then we done in analysis in the bacteria. So this is one reaction that I've been trying to do for the past maybe 20 years. Okay, so we try to mimic this process. Okay, so this is a very powerful enzyme. Okay, it's called synthase. They can zip up this molecule. Very simple molecule, no ring, only just one epoxide here. You zip out in one step to construct 1, 2, 3, 4, 4 rings here. And you can see that we only construct 1 out of 128 possible isomers. So there are 128 possible isomers. The enzyme only construct 1 out of it. Not only that, just in one step. Okay, and then you can construct maybe tetracyclic and dicyclic natural products, highly substituted carbon bonds, which are very difficult to construct. And not to mention that this reaction is done in water. Okay? Our body uses water as a medium to do organic transformation. Something that always impressed me when I was a student. Why organic chemists need to use organic solvent? Okay? Which is smelly, flammable, sometimes even toxic. Okay? So I won't go through this talk today. Okay? Basically, we mimic this process. We published a lot of papers on that, but we stopped recently. So we found when we find that something is not moving, then we'll stop for a few years and see. Then we reflect on it and hopefully come back again. Okay? So this, we actually come up with methods to construct this one quite efficiently and publish some papers, but we still cannot beat enzyme. Okay? And there's one process in enzyme that was very effective is that when they construct these type of reactions, do this reaction here, they were able to do it in the chair-boat chair. Okay, chair-boat chair. When you talk about boat, it's very difficult to translate for organic chemists. Chair is easy. And up to now, there's still no chemists that can do a chair-boat chair part that mimic the enzymatic process up to now. Professor Corrios, who worked on this project for many, many years and still cannot do it. We tried it for a few years, also failed. Also cannot do it, okay? It's not easy to give that project to students. When they see that project, they don't want to do, okay? They easily run away. Especially those in China, even worse, because I have a lot of Chinese students in China, okay? I have about 100 over students in China right now. When you give that project to them, they know that you cannot publish. Tough. And without publication, they cannot grab it. So they usually very scared of getting that project. Singapore is still not bad because even with no publication, you can grab it, okay? So that's a good thing about Singapore right now. You can do very risky projects. Not saying that things against Singapore. So we're still working on that project. Another reactions that we work a lot is called amino group migration reactions. In our body, enzyme is very powerful. You're able to do some very difficult transformation, changing an alpha amino acid to a beta amino acid using this enzyme called amino mutase. Very powerful enzyme, okay? A group, you see the amino group, can migrate from this red color to the blue color or the blue color to the red color. And that is not easy to be done outside the biological system. Not only that, they can migrate this amino group, they also do it in a very stereospecific manner. That means the stereochemistry is precisely preserved, okay? It's also very tough in the chemistry. No report in organic chemistry. So nobody done it outside the biological systems. So our group actually succeeded. I won't go through the detail again. So we came up with a strategy using copper catalyst and oxygen. Not fantastic because we don't want copper, it's a bit toxic. So we were able to migrate this nitrogen from the blue color to red color in 2010 after spending about 3 years working on this project. Later on, we found that we can also replace copper with just iodine. So we can totally remove metal from our reactions. We're able to do this reaction now with iodine to migrate these reactions. So during the process of this, studying the mechanism, okay, we came up with another methods, okay, to do alpha amination reactions. I won't go through all this, I'll just give you a sketch, okay? I'll talk about water. I'll come back to water later on. So you look at the way we do organic reactions, okay, as organic chemists. A lot of times you need to use toxic and flammable organic solvent. That's simple because most of the organic compounds dissolve in organic solvent. If you don't dissolve in organic solvent, you cannot do the reactions. It doesn't hit each other. It doesn't react. So it's very hard. We need organic solvents. Okay? But in our body, reactions are done in water. Okay? And that's surprising. Okay? A lot of times we need to do very acid or basic conditions. But in our body, it's done in neutral conditions. And given very clean neutral conditions. When the reaction doesn't go, as a chemist, students say, just reflux it, okay? It doesn't go, we add in things again, okay? But in our body, the reaction is done at our body temperature. We don't do reflux, okay? We don't cook things at the body. We just do it since it's the body temperature, okay? Basically. A lot of times in our body, we don't use matter. Sometimes we use matter, but a lot of times we use metals, okay? So, it's very difficult to do matter-free reactions. A lot of times we use matter to catalyze reactions, to replace enzymes as a catalyst. We have problem with selectivity. So enzymes do reactions very effectively. It's just 100% selectivity. Either chemoselectivity, either stereoselectivity, whatever. It just gives you one precise job, a lot of times, okay? But in our case, a lot of times you get mixture. Okay? Mixtures, unless you come up with good catalyst, and Prof Khan just came up with a very good catalyst, just got a paper in science, okay? So it's a very good catalyst, powerful catalyst to do this type of selectivity. A lot of times you use toxic chemicals. But if you do reaction in the body, you do toxic chemicals, you die. So all the chemicals exist in our body has to be safe. Okay? So that's the difference between an organic chemist and an enzyme, our body as a chemist. The way we do things are very different. So if you can mimic this type of process, I'm sure it's going to be an efficient process. Okay? It must be a clean process because you don't produce toxic chemicals in our body. So, water. So I'm interested to focus on water. So in the 1990s, when I first came back, at that time, we do not have an aircon in the lab. The lab is like oven. In the afternoon, 3 o'clock. So I came from a place which we work in aircon. In Japan also aircon, in the US also aircon. But when I came back, all the professors say, don't work in aircon. Organic chemistry is very dangerous. Like people like me, I cannot work without aircon, okay? So it's so humid, it's very difficult to do organic reactions. You have to flame dryer flask, you have to put everything in the oven, but when you take out, it becomes humid. It's very difficult to reproduce reactions because a little bit of water sometimes destroys the reactions. So I thought maybe it's time to look at water as a solvent to do reactions. If you do reactions with water, you don't need to worry about the humid weather in Singapore. You don't need to worry about the hot temperature, okay, all these things. So we were all doing reactions in a wooden fume cupboard at the time, one fume cupboard that will stop at 5 o'clock. Automatically, electricity. Okay? That's the time, okay? So we thought water is nice. Why? Again, high school student can do the reaction. And we also have high school students. My first student was a high school student from India actually, from RJC, came weekends to do the reaction. So it's very easy if you can do reactions with water. Not only that, it's cheap. Okay, it won't cause fires, no flame above, polar. Okay, I won't go through all the advantages. But as an organic chemist or the students, you always have a fear of water. When you see water, you get scared. Why? Because many of the organometallics reagents that we use in organic synthesis are not stable in water. You touch it, something catches fire. So there's a fear, okay, water. Nobody say, hey, don't do water, it's scary, okay? And then most organic compounds are not soluble in water. If it's not soluble in water, you cannot do reactions. Totally, you cannot knock each other, there's no reactions. So it's tough, okay? And then you say you use reactions to do in water, by the end of the day, you use organic solvent to do the extraction. You defeat the purpose of doing reactions in water. You still need the organic solvent. You do column, you do extraction of organic solvents. So that's still interesting. Then there are a lot of things not well done in water reactions at that time. Not much done in still chemical control, and cannot use these reactions to synthesis drugs here because there's so much information about water-based reactions. Okay? And waste in waters are not easy to treat. Because most of the industry, you talk to them and say, oh no, I don't do water because the waste in water, we don't know how to do treatment. So there are still a lot of problems associated with water-based reactions. But despite all this problem, we decided to start this project, this research program. So the Nobel Prize-winning reactions that I mentioned here, we look at the first reaction, that's Grignard reactions. Grignard reactions are very powerful reactions. You can convert the carbon delta plus here. If you insert a metal, it becomes a minus. So you can reverse the polarity to form a C minus. So C minus and C plus react. If you cross the activation energy, you form a CC bond. So a very powerful reagent because it creates C minus carbon ion reagent. And with that, you can react with a lot of electrophiles to form CE bond, okay? But the problem is that this Grignard reagent is a Nobel Prize-winning reagent, okay? But it's extremely sensitive to water. So the first thing we ask is that can we beat this reagent, come up with a better reagent that can work in water, but behave like Grignard? Very easy to make. That's one thing. It's powerful because it's very easy to make. Whether this carbon is sp3, sp2, sp, just insert it, we revert the polarity from plus to minus. Very easy to do. So we thought, can we come up with a method? So we go through literature. At that time, very difficult to do your own research. What you do is you try to copy some research first to start off, okay? So we decided to look into methods, different methods, and see what are methods can do reactions in water. So we found that these three methods is known: tin, zinc, and indium. We have done it, okay? We are not the discoverer of these things. Tin, I'm very scared of tin. Carbon tin compounds are extremely toxic. Okay, when I smell it, I get headache, okay? So I decided not to use tin. Tin is out. Zinc, not bad. It's still cheap at that time, okay? Cheap. But a lot of people study on it. There's a lot of limitations. So I decided to look into indium. And there was very little work on the indium. Okay? So actually I was very lucky at that time because I was so poor at the time that I have no money to buy chemicals. So I went to the chemical store. You know, a lot of time I went to chemicals to search for like trash can, you know. A lot of old professors retired, they throw all their things inside the chemical store. So I searched around. I found a big bottle of indium powder. And that changed my life, okay? The indium powder was actually left behind by the inorganic professor. So retired. So I took that big bottle of indium powder and said, this is the one that will save my life. My tender depends on this bottle of indium. That's true. Okay? So with indium powder, people have found that it's very easy to react and insert into C bromide to form this C indium bond. So you reverse the polarity from delta plus to delta minus and use the reagent. You can do it in water. Okay? People have found out. So when I saw this paper, I was very impressed at that time. That paper was a different paper, not this paper. Okay? So we decided to go into this area. We did a lot of studies to make sure that these reactions, we studied all the scopes, the limitations, all the stereochemical outcome, everything. So that right now people can use these reactions to do synthesis. And also very happy recently, this month, Professor E.J. Corey published a paper on indium chemistry. So my supervisor started to do something that I was doing in the 1990s and 2000s. So, but he published in Jacks, okay? Just came out this paper, just came out here. So anyway, we published a lot. We did we actually summarized all our works in the chemical review, our 900 publications. Spent 2 years writing. Usually I don't write review article. I think I'll write review article when I retire. Usually, okay? But somebody invited me, and I promised. I spent about 2 years 900 publications. Finally, we summarize all our work plus other people's work in this review. So today is not my focus, but this is the first method that we can use to replace green but indium is too expensive. It can never be industrialized. So I decided to move this project aside, okay, and move on another project. Then, during the time when we were working on indium chemistry, we discovered that indium salt, not indium right now powder, but indium salt can be used, it's actually stable in water. And we were surprised, so we checked the Merck index, it's like a Bible in organic chemistry, and found that indium salt is actually stable in water. So we asked the student, maybe we can use indium salt as a catalyst right now, as a catalyst, okay, to promote different reactions, like the way enzyme work in water. So indeed, this indium salt is a magic catalyst. It reacts with all the different catalyzed different CC bonds, CX bond in water. So we published this paper in Chemical Hot Paper 996. We received a letter from Japan. Now we realize that suddenly people open up. Okay? My competitor start to write a letter saying that I'm not happy with this publication. I think there's a problem with this publication. So people write you this letter, then you realize that you're not bad. Okay? Somebody is competing with you, somebody is noticing your work right now. Okay? So we go through many years of writing. Not easy to fight with Japanese professors in Tokyo, okay? They have a lot of resources, okay? And now we become good friends. Not that good, at least we shake hands, okay? We move different direction, okay? But then the key thing is that you still need to use indium complex to do water catalyzed reactions. Indium salts to do like Grignard reactions. We ask the next question is that can we do reactions like in our body, no matter, nothing, and do the reactions? And this is easy said than done. If the student do the reaction, it doesn't go, the first thing you ask is, Professor Loh, can I reflux the reaction? Oh, no. It has to be room temperature. Can I put in other catalysts? No, it has to be metal free. Can you do at other pH? Also cannot. So what to do? Stuck. No ideas. Do other project. That's the real idea. So it's very difficult to change the conditions if the reaction doesn't go. You have to design properly. Another thing that we're interested in this reaction is that we wanted to do functionalization of protein. Something that I wanted to do many years when I was in NUS, but I'm not able to do it because I don't have the expertise in protein. So I went to Columbia Medical School. And that was a good time when I was there with my family. Every day we go for good food, you know. But then we talked to a few friends there. They wanted to do protein chemistry. Like I say, these are some people you read. But it's very difficult because no students can do it. We don't have facilities. So when I came back to NUS at that time, I decided to collaborate with a friend in Novartis. That's how we started, okay, on the protein chemistry work. We'll talk about later. So in the water-based reactions, basically we can divide them in three categories, three parts. The first one is the water-stable organometallic, like Grignard reagent. Okay, this is one category. The second is the water-tolerant Reese acid. Okay, using metal complex as a catalyst that works as an enzyme in water. We're still working on that. We're trying to design a chiral indium complex that can work in water. Struggling for many years, okay? That's why it's a tough project, okay? But now we shift gear to here, metal-free systems and doing biocompatible reaction conditions. That means no matter and water and no byproduct, hopefully, okay? So this is our contribution in this area. The first part is organoindium, then suddenly the other one, the second part is on the water-tolerant acid. And today I'm going to focus mainly on the design of new biocompatible reaction conditions. Reaction that we can think that can be done in the body. So our ultimate goal is to do reaction in the living cell. If you can do in the living cell, and then come up with a drug and destroy the cancer cell. Do it in the cancer cell and destroy it, and that will be interesting. Obviously, if you can actually do the reactions and revert cancer cell back to normal cell, it will be more interesting. It's a big dream, okay, but it's not easy to do, okay? You can always dream, that's a good thing about doing research, okay? So, when we do drugs, design natural products, a lot of times it comes from natural products. I won't go through the detail. I mentioned just now there's one Taxol. It's from blood, okay? Or from Chinese medicine, whatever. A lot of times from there, they design new drugs, okay? Another way to design drugs is actually, new drugs, is actually to target, or the way to destroy the virus. For example, when I was a student at Harvard, my first project given by Professor Corey was to design a molecule that inhibit the replication of virus. And he told me, it's a secret project, you cannot tell anybody. I like this word, but those people it's a secret project, they get excited. Although it's not that secret. Secret. Don't tell anybody, okay? Oh, I get excited already, okay? So he told me it's a secret project. Don't tell anybody, okay? But it's an interesting project because you target. It's very interesting. At that time, there was a paper published by Harvard Medical School on the way the HIV virus replicate. They have to cut one bond, the amide bond, to replicate, to make their own cell. Okay, they replicate, right? So we designed a lot of molecules to stop the replication. And before we completed the project, there were 3 drug molecules came out from different drug companies. Same thinking, exactly the same thinking, okay? They were too fast. There are 100 people working in this area. You only have 2 or 3 people working in this project. That was an interesting experience, okay? How to actually design a molecule to target, to inhibit the replication of virus. At this moment, there are so many HIV protease drugs right now, many. Actually, all designed based on the same thinking. So you won't die of AIDS. You still survive, okay? You won't die, okay? You can live quite long right now. Anyway, this is 2 ways of getting drugs. Another way of doing drugs is actually using a delivery system. And then you hook in some sort of molecule, toxic molecule. So this delivery system can be anything. It can be a nanoparticle, can be antibodies. This thing will actually deliver the drug to the cancer cell and then boom, and destroy the cancer. Obviously, there are also controversial methods, like recently in China, we have this gene manipulation of newborn baby, which inhibit the baby from getting HIV. Very controversial, okay? It's big news right now, okay? Now we can make superhuman maybe someday, okay? But it's dangerous, okay? So it's playing the gene manipulation. This is the biological method. What I'm saying right now here is more the chemistry methods, okay? So what we wanted to do is that can we look at this type of molecules, delivery molecules, and then link that with a toxic molecule of the drugs, and then deliver it to the cancer cell. This is actually one of the projects that we started 10 years ago. So to do that, we are not the new one. There are many people working on different bioconjugation methods. Professor Sharpless came up with this concept called click chemistry. So what is a click chemistry is that he has this functional group called azide, and then the other group is this alkyne. He can actually click them together, like click, okay? Using a copper catalyst to do this sort of thing. And this is actually very big. People think that he may get a 2nd Nobel Prize for click chemistry, but I don't think he get a Nobel Prize. For simple reason that this reaction here, there are a lot of problems. So usually when I teach a course in undergraduate course, people do microscope. I always say the advantages and disadvantages of method. Always say that. I prefer to know more about disadvantages of the reaction rather than the advantages and the good things about the reactions. So you look at this reaction here, it's fantastic. You can actually click different molecules on it, a different tag. It can be a color compound, it can be a drug, whatever, to click onto the biomolecules. But the problem is that you need to use copper salt, and copper salt can be toxic. Okay? The other thing is that they use matter. Matter can destroy the conformation of the 3-dimensional structure of the protein. And the 3-dimensional structure of the proteins are very important for the function. Okay? If you use too much matter, you destroy it. Okay? You need to pre-functionalize the substrate to put the azide group into the molecule, the biomolecule, or put the alkyne into the biomolecule. So you need extra steps. It's not easy to do. So people come to design new this type of click chemistry. But with this design, they're using a very plain alkyne with 2 F group here. So using this type of reagent right now, he can do the reaction without any catalyst, no copper. Very straight. But these are not easy to make, very tough to make. So still not many people using this reagent. Okay? So this problem of click chemistry is there. So we thought, can we first enter this area first using water-based reactions, functionalized protein. So to do that, we started off with very simple protein, cheap protein, myoglobin that you can easily get cheaply. And this is the terminal, the glycine. And we know that you can actually functionalize this amine very easily using this reaction here to get the aldehyde. And this aldehyde is a very reactive aldehyde, very reactive because of electron withdrawal group here. Then we decided to use our indium chemistry and say, okay, we throw in indium and relation in water, we do the reaction C-bond. Fantastic, we got a product. A CC bond was formed on the protein. But the problem is that when we measure the structure, 3-dimensional structures of this protein, we found that they were actually partially destroyed. That means that indium matter is not good for protein. So that came out and said, okay, now's the time that we remove matter totally. Then we recall some of the work that we published in 2000. We found that we can actually do a Mukama aldo reaction, a CC bond formation with this side lock in the middle and this aldehyde here, delta plus, delta minus, to form a CC bond here to get this beta hydroxycarbonyl compound. In water with no matter. At the time I wasn't bothered with this, just publish a paper here, not that interesting, okay? Then we say this reaction doesn't even need a metal catalyst. This reaction is discovered by Professor Narasaka actually, who left right now. He was here for many years in our CDC from Japan, okay? Professor Mukayama is the one that, his boss, just passed away. He was waiting for Nobel Prize, unfortunately, okay? So this is a very powerful reaction, but they use Lewis acid, and they cannot use water. Okay? So in this case, we were able to do it very nicely to get CC bond. So we thought maybe we can use these reactions on the protein functionalization. Okay? So we do these reactions on neutral pH, in water, atmospheric pressure, body temperature, metal-free, very fast reactions, and no toxic chemicals. Okay? So we go through, I won't go through the detail of the experiment, and finally we found that with just water and P-butanol here, we can obtain the CC bond formation product with 90% yield. Okay. And we found that the three-dimensional structure of the proteins were preserved in the reactions. So no matter, no heating, the protein structures was actually preserved. So we're able to put in different type of molecules onto the proteins. So we can introduce azide into the molecule, we can do quick chemistry, we can put double bond into the molecule, we can do olefin metathesis. So we can introduce different type of fluorescent compound, the dye, so that we can do the bioimaging with this type of reaction. So powerful methods, but there's one problem. The first problem is that we need to functionalize the protein first to introduce this reactive intermediate, which is not interesting. We want to directly react on the protein, not functionalize it and then do the reactions. So that increase one step. So we thought if we can functionalize one of these many functional groups on the protein, that will be interesting. So there are many functional groups on the proteins. You have different amino acids. You have tryptophan, you have thioglutamin. So in order to introduce a drug molecule or some sort of imaging molecule, you choose the amino acid that's rarely occurred. That means the least. Okay, so that you introduce those expensive chemicals only to just one functional group, rather than so many functional groups, wasting all your precious compounds. Okay, so you choose those the rare abundant type. So we chose cysteine, the SH here, okay, which is rarely occurred in the protein. So we have to do this reaction again under water, neutral, room temperature, metal-free, and fast. Fast and also must be highly chemoselective. Only react with the sulfur without touching the other functional groups. Must be very selective and very fast. Remember that proteins or enzyme reactions in the body is very dilute, extremely dilute. So the reaction has to be very fast. So a lot of people come up with this type of method. We are not the first one. So people design reactions that can react only with sulfur. And this is a very powerful reagent, malate. This malate amide, last year when I was called to nominate the Nobel Prize, I nominated these reactions, okay? I think it's a very powerful reactions. They only react with sulfur without touching the amine groups or other functional in the proteins. And it's used a lot to make biological drugs. Not only that, it's also used in material science to link materials, particles to different things, okay? Very powerful. But they are also powerfully associated with this linker, we'll talk about later. So we decided to design our own linker, okay? So I'll cut short all the stories. So we designed a very simple reagent. We decided to use the allylic amide, okay, to do the reactions. And we found that this reagent actually selectively reacts with the sulfur without touching the amines. Extremely high selectivity. And this is done in water, no matter, room temperature. Very selective. I'll just cut all this story short. So you can see here, this one is the SH and the amine. You only react with the sulfur. No reactions with the amine here. Same thing here. OH and amine, no reactions. Okay, amine, no reactions. Highly selective only on the thiol. Even this terminal SH also react very nicely without touching the other group. Internal SH also works nicely. Again, using phosphate buffer, pH 7.2, very selective, only with this sulfur, without touching the other functional group. More complex also works. Again, we just want sulfur without touching the other functional groups. So very selective. Okay? So then we started to introduce colored dye into this protein. So hopefully we can use it for bioimaging. So we cut this protein here, this two strand here. We can the sulfur linker here. We can cleave it. Then we got roughly 1, 2, 3, 4 sulfur here. Selectively react with our linker. We introduce green dye, yellow dye, or even red dye. Okay, so we can put bioimaging materials into protein. So we actually, after we published a paper, then we received a few letters actually from company. They wanted to buy our technology. Surprising, I thought we just do basic science, okay? So I checked out this letter, this company. Why are they interested in our compound, in technology? So I realized that this company is doing research in the area of what we call an antibody drug conjugate. So we started a research program. We don't sell that, right? They wanted to buy at 40,000, so 2 liters, so we didn't sell the technology. So antibody drug conjugates. That's right. I didn't know anything about antibody drug conjugate. It's actually an antibody that's linked. Okay, this antibody linked to a drug. Okay, and this antibody will bring the drug to the targeted cancer cell delivery system, and then go in and kill the tumor of the cancer. And there are actually right now 4 of these drugs in the market. So I got interested in this. So I watch a lot of YouTube every day, antibody drug conjugate. I learned myself actually. After a few months, I became expert in antibody drug conjugate. Okay? I think biology is still easier to learn than chemistry. Sorry, the inside here is about biology. But it's true, you can learn from the YouTube. So we threw a lot of antibody drug conjugate. A lot of power, okay? So we're able to know the problems, and we decided to look into how to design this linker. So we are interested to use our technology as a linker to link the antibody, which is a protein, into a drug, a very toxic compound, okay, to make new drugs, okay? So right now there are 4 of them in the market, and they are very expensive. One treatment, I don't think Singapore has a drug yet, only in the US. So expensive that it's very difficult to afford these type of drugs, okay? But it's extremely, can be very powerful for breast cancer and ovarian cancer, 2 types, okay? There are right now 4, but the structures are very similar sometimes. So there are 2 of them right now extremely useful for breast cancer and ovarian cancer. So you can see that they have this antibody, it has linker. And the linker they use a lot of times actually is a maleimide linker. So we say that maleimide is our enemy. So ours is an allylic amide. So if we can beat maleimide, then if we replace all the maleimide, the center one, the linker with our linker, it becomes a new antibody drug conjugate, become a new drug. We ask a patent lawyer, they say it's a new drug. Very simple. It's easier to design a new drug just by changing the linker rather than from small molecules from natural drugs, which you design, try and error, you design for 10 years, 15 years already. But with this type of design, it's easier. You just change the linker or change somewhere here and become a new drug. So we decided to change the linker, replace it with our linker, the allylic amide linker, and come out with new drugs. Okay? So to cut the story short again, it's a very big market. Now there are about 40 of them right now in different phase 1, phase 2, phase 3 trials. Okay? And very secretive. You can't get much information from customers. Many of them right now, because it's easier to get the drugs compared to those using small molecules. Okay? So maleimide has problems, linker. If you look at this type of linker, maleimide, very selective with sulfur, very good. But this thing sometimes can be hydrolyzed, it will open up. And also it can do lateral mica, it can go back and exchange, causing problem. So always we find problem with other things and then see whether we can beat those problems, okay, overcome those problems with our linker. So ours, this is our linker, allylic amide instead of the maleimide. Ours is very robust. That means we put this compound, the drug, we make it, okay, antibody drug, put it in the blood plasma and circulate, it's still very robust. Robust doesn't mean it's good. Good, okay, robust good in the sense that it's not, maybe toxicity can be reduced. But when you go into the cancer cell, it cannot be released. Okay, that is useless too. So we all found. So our first project that we got some support from NRF is actually to replace the maleimide linker with our linker. Okay, all the drugs in the market. And we were very disappointed that when we replaced all our linker, no effect, too robust. okay? Doesn't break inside the thing, okay? Very disappointed. But then, okay, so very luckily, when we do some try and error, sometimes try and error is better than rational design. And so when I was in Harvard, the professor was calling it rational design, rational design. But I come to Singapore, all my rational design failed. Maybe I'm not smart enough, okay? So we design something, spend many years and then it failed, okay? So try and error to me sometimes is more interesting. So we decided try and error, we find one molecule, okay, one ADC, antibody drug conjugate, is very effective towards breast cancer. We have not gone through the toxicity test, but we believe that if you replace small things, okay, on this type of known drugs, okay, and found similar effects, it can be an interesting drug. We have not moved to the toxicity testing. And it's a lot of money because antibody is extremely expensive. Okay, it's not like organic compounds that's cheap. Because sometimes you use humanized type antibody. That means it can be used in human. It's very expensive. Okay, so not used. We are not as rich as other. Now we are very poor. Chemistry right now is extremely poor. We are not getting enough support from Singapore government. So then we found that in this antibody drug design, it's very important that your molecules or your drug molecule, this is the toxin, okay, or the payload, the number or ratio to the antibody is important. It cannot be more than 4 to 1 antibody. But the problem is that the sulfur group on the antibody, a lot of times the antibody you use has about 8 sulfur tire group when you break it. Sometimes 6, sometimes 8. So in order to get 3 to 4 to 1, you have to selectively control your reactions. And that's why it's very expensive. This is the drug. But if you can design a new linker where you have 2 sulfur reacting to deliver only 1 payload or drug, then no matter how you do, the maximum you get is 4 to 1, am I right? So very easily we have succeeded to design 2 new linkers that can do 2 sulfur, 2 payload to 1 drug. 1 in Singapore, 1 in China. Okay, we are writing out the paper and filing papers. But to file patents, we need to do a lot of things. Okay, so the China one has 1 design, and Singapore 1 design. So in China, I have a lot of collaborators. I have 19 to 20 collaborators and hundreds of students working in this project. Okay? So let me move to another project. So when you do biological reactions or in the biological body, the product that you get, you don't need to do isolation. Our body don't do isolation. After you make the molecule, you use the molecule directly to do biological things, okay, functions. But for organic chemists, after you make it, we need to do extraction, column chromatography to get it pure. So there's always the thinking, how do you do reactions in water? Totally water, 100% green. Don't even touch organic solvent. So this is done in collaboration with another professor in China. So I told him, you just do on water-based reactions. I don't want to see organic solvent. That's it. But this is a very smart guy. You know why? I collaborate with him because he was a postdoc of my enemy in Japan. So I recruited him and joined my group, the one who wrote me the letter. Okay? So he was very good. So he was in China. So at that time I was the dean, okay? So I walk around and see this guy was very poor. He's no student, very poor. I said, let's join force, okay? Come, and do this project, okay? And he did it, okay? So he worked on this, trying to get these reactions, trying to get this product, analytic sulfone. So I'm trying to get analytic sulfones. They're very important compounds. They are used for different things. I won't go through details again. So to make this compound, people use very complicated methods. People use methods. The reactions are not atom economy. That means a lot of byproducts. Okay, and sometimes you need to reflux. You use metal complex. Okay, these are the known methods. So he came up with a design. So he said that can we use this sulfuric acids with just the analytic alcohol, no matter, do the reactions. You see the elements are 100% almost incorporated into this product, which is called by atom economy, and the byproduct is only water. And this reaction is done in water ethanol, which is all safe. Okay? Ethanol you drink as a process. Okay? And it's done at room temperature. So I won't go through again screening conditions. So you're able to do it in water ethanol to do these reactions. Okay? Very good. And the good thing about these reactions is that all the product that you make actually solid in water, almost 99%. That means you crush up after the reaction. So you crush out, you just do a filtration. No need to do extraction, don't need to do a column chromatography. So the first time we see that the reaction is actually 100% green. No organic solvent. Reaction done, product crushed out as solid, filter the product. And we even do it at gram scales, okay, of some of the reactions. This one here, we do filtrations. Okay, demonstrate gram scales in 3 grams, okay? More complicated one, I won't go through it. Here, okay, you can also do complex system here again. Even a drug molecule can be easily made. So we think that this is one of the 100% green process, which you don't really touch organic solvents. The reactions, very interestingly, when we do a molecular modeling calculation, we found that the water, without water, the reaction doesn't work. Surprising. That's by pure ethanol, no reactions. So we found that actually water actually is a catalyst of these reactions. It actually catalyzes the reactions, not just as reaction media, but also function as a catalyst to do the reactions. And we did this calculation here, we found that this is most probably transition state. We're still not sure. So we're trying to design new reactions where the water not just function as a media, but also as a catalyst for the reactions. Okay? You see extremely green, metal-free, room temperature, very good yield, very good selectivity, and broad spectrums of substrates. We found that most probably water is involved as a catalyst. And that opened up another area. So now we start to design new reactions where water catalyzes reactions, okay? So this paper was highlighted. Not only does the use of water works towards making this process green, but it actually acts as a catalyst or promoter to promote these reactions. To me, that's more interesting in terms of science part. So now in my group, we are trying to design a toolbox of CC bond, CX bond that can be carried out in pure water. No extractions, no column chromatography to get the product. Once you have that toolbox, okay, it's like I'll go toolbox later on, okay? Then we can use this one to make drugs and complex molecules without even touching organic solvent. That's the power passion that hopefully can be done before I retire. Okay? So I demonstrated that we can do CC bond reactions on the functionalized protein in water to get this CC bond and keeping the 3-dimensional structures of the protein. Then we decided to look into direct functionalization of the protein. We designed a linker, a new linker that belongs to us, okay? This linker right now, people start to use our linker. And this linker can be used to link antibody, and they react selectively only with the sulfur group without touching the other group to introduce important molecules such as drugs or target compound. Then finally, we discovered, we thought this will be really a truly green reactions. It was CS bond formation. Now we are working on CC bond, other types of reactions transformations in water. And we also working on actually trying to come up with methods where we can actually purify our compound using a material, a sponge, that only suck out the organic compound by not touching the water. This is known. This is used for what do you call it? Spillage of the oil. Okay, you can use sponge to suck out the oil without touching the water. So you can do that. We can actually purify reactions in water. Don't need to be solid. So I've seen a Chinese paper just came out very recently using wood. They were transforming the wood into sponge, and then they put something on the sponge, and this sponge is using something to suck it in the mixtures of organic solvent and water. You only suck the organic solvent without touching the water. So that is another thing that we need to work on. That means you don't even touch any organic solvent. After the reaction, you put the sponge with your pipette, suck out pump, you suck out your product. Okay? But the reaction is clean. Okay? So that's what I'm saying. We wanted a toolbox which should have many, many different reactions that work in water with no methods, okay? And no organic solvent extractions or purifications. And use this toolbox, you can construct any molecule that you want. Okay? So right now, I intended to start a project again. Okay? I'm trying to find students. Not easy to find students. You don't get graduate students. I only have 1 graduate student right now. I used to have 30. But now, I don't know why NTU is getting very poor. Most students, okay, we are moving the other way around, and the one cycle. I think we're going back to the back cycle. Hopefully come back again, better cycle. So we're trying to actually give every student in my group a total synthesis of complex molecule. For example, prostaglandin synthesis, a very important drug in the market. They have like maybe 10 steps. Every single step can make it to be green. No water, and no organic solvent, no metal complexes, green, every single step. And they will come up with a good PhD thesis. So I'm giving every student maybe one very interesting synthesis of complex molecule for every project, for PhD project. You finish it, you graduate. Okay, if you don't finish, you stay. Another thing that we work on other research programs, many other research programs, but today I'm focusing just on water. Another thing that we are interested in, we work for many years, try to convert wood to drugs. It's my dream. A lot of dreams. My student cannot catch up with me. It's scared. But I'm very ambitious. I'm very daring. Yeah, I think you talk about student, I'm very daring. Just hunt down. Maybe the way you grow up change the way you do research. Maybe I'm also very aggressive and stubborn. So I used to do tough project, just throw, don't bother. So if we can convert chopstick to drug, that will be interesting. So we started this project, we spent about 3 years to 4 years, making some progress, not a lot of progress. I won't go through the details today, okay? Every one day we don't need to start from oil or petrochemicals, we start from wood, and then make drugs, okay? And people ask the question, some of my son asked me, you make this not a drug from wood, can you be eaten? Actually, they're the same thing, but people would have different concepts. You have to change the mindset, Making drugs from wood, strange, sounds strange, okay? I think the day will come when the petrol price or gasoline price become too high, you have no choice, you have to start with using wood, okay? But now, gasoline price is still okay, it's still reasonable, okay? So other project we're working on, I think Chung Hong also very interested in that. We are doing this one in China right now. We are going to start up an AI, okay? Artificial intelligence. I think it's very important. I think it's very interesting. Singapore should also start it. We are going to start it very aggressively in China. I have no choice. I cannot survive in Singapore. I have to go around asking for people help. China right now has money. They are giving me maybe 50 to 80 people to work on certain project easily, okay? In Singapore, we have to talk to the president maybe one day to get more answer. Why are we doing that and give away our things, okay? Anyway, I think it's coming. It's coming aggressively, okay? AI means what? That means that this robot may be able to replace our student. That's what they say. Okay, so there'll be a lot of robots in the lab. After that, then you just key in, screen this thing for me. Then you work 7 days a week, 24 hours a day. So make sure that when you study right now, you have to be better than the robots. Robots can do what you do, better don't do it, okay? You have to do things that robots cannot do. That means think more creatively. And some robot may be able to think. I was in China, I see robot dancing. Now they have dancing group of robots. All robots on the floor dancing with the music. Okay? And they start to think, And then the kids buying robots, mobile toys. You give them a robot, you press. What's the weather today in Nanjing? Oh, 17 degrees, okay? Can you bring me something? Even the robot cleaning right now. I think a lot of people right now have bought cleaning your house, okay? So things will change, okay? So please, I think it's coming very aggressively, the AI thing. And other things that we are going to do is that maybe one day we do organic synthesis. I always wanted to replace the way we do like a photocopy machine. A photocopy machine, when you copy the picture, you can't come out the same picture. A different toner, that's it. I spent many years trying to design a Xerox machine for organic synthesis. I thought we'd make it to a certain extent, but nobody accepted my paper. Until we published in a very shitty journal, okay? And then finally they called me to remove the word Xerox machine. I think the day will come also. We will replace organic synthesis like a Xerox machine, okay? Whatever picture you put on it, it come out the same picture. But organic synthesis, we spend make so many years and then collapse again, make again. Wow, very troublesome. Things will change, okay? So there are many other things. That's why I mentioned to you that hopefully we'll design a drug that can change cancer cell back to normal cell. I think that's one thing that hopefully can be done before I retire, hopefully. 10 more years, okay? And you have a molecule that delivers the cancer cell and revert the cancer. There are certain cancer cells that can be reverted back to normal cell, not all. Not just kill cancer cell anymore. So maybe one day you put your tea, a lot of Chinese people like to drink tea, put a compound inside there drinking. Cancer cell come out, back to normal cell. Cancer come, every day you can live forever. So that's something that I think will come also. Hopefully there will be a cancer cell that can revert back to normal cell. Not many. I think there are one or two, hopefully. I read some articles, some Japanese claim there are some, but it's not proven yet, okay? So again, we are doing reactions that hopefully will beat many of the Nobel Prize reactions. We have reactions that want to beat Wittig reactions. Wittig is the Nobel Prize winning. We're also doing reactions that wanted to beat the coupling reactions. We're also working on that for many years. Still working on it. The day will come, hopefully we do coupling reactions that can very easily, as compared to the one right now. We're also doing reactions that hopefully can beat the olefin metathesis reactions. we are going towards that area. So this is another area. Reactions, find the reactions, beat the reactions. Hopefully one day we beat one or two, and then you become industrialized. There's another dream, okay? So this is one of the reactions we're working a lot. So classically people do coupling reactions, volcanic halides and metal. We remove the metal and halide and do cross coupling. So I'm working on this one for many, many years. I just wrote a highlight actually, especially golden series in not a good journal, but simply because of implications on these coupling reactions. Okay, without metal, without halogen. Okay. I have to first of all end my talk by thanking all my collaborators. I lost the names too many. Cannot even sorry about that. And most of the names I mentioned, the publications I mentioned here, in slides. There are so many collaborators, students. I have 3 groups right now. One in USDC in China, one in Nanjing Tech in China, one in Singapore. Okay, but I'm building another group hopefully in China. Okay, and we are recruiting. I'm recruiting for them. Okay, so we are going to set up another institute in Taichung, Suzhou, from Xiamen Xi'an Institute. I'm helping them to set up the institute. I'm not. If you're interested, we can talk about that. Okay. So collaboration, thank you Sim Mengang for bringing me into the world of protein. He's an expert in that. Okay, and then Novartis, Thomas Keller from Novartis, they actually allow us to use their facilities, okay, on the protein. And then as I mentioned, Xie Pei Zhong, the one on water-based reaction, the last part. Okay, I have to thank again for the financial support. For many years, I've been getting from Ministry of Educations. My recent years have been getting very tough for chemistry. I don't know why. Maybe we're not selling enough of the work. We need to go around selling more of work again. A-Star also, I'm not getting support from them for many years. But I have to thank the Division of Chemistry and Biochemistry because, as I mentioned, I was the first head. Okay, and I got a lot of support from this. I also get a lot of support from Swing. So you have to support this. I cannot decline him when he say call me to give a topic. I have to say yes. Okay, so since NUS days, okay, he's the one who gave me multiple promotion. Okay, so I will thank him. Okay, University of Science and Technology. I've been there for almost 8 years already. Okay, a big group there, about group 20, with one associate professor taking care of the group. Nanjing Tech, as I mentioned, I'm collaborating with 19 professors. I usually don't set up my labs, okay, so I collaborate with them, and then they do half my project, half their project. Okay. I also thank even China funding agents actually supported my research more than all this combined. So I don't know why. So they give me more money for my research grant. Thank them as well. And again, once again, thank you very much for kind attention.
Now the floor is open for questions. Let me start by asking second question. How do organic chemistry? Because when I was a student, the emphasis was on reaction mechanism. All the different kinds of reaction mechanism. But in this talk here, you never spoke about reaction mechanism. You was like cooking, okay?
No, this audience are more general. So not general audience. So I didn't talk about the reaction mechanism. Because if I put out the mechanism, you get scared. So I decided to remove all my reaction mechanism. My reaction mechanism is very critical. Because when you design a reaction, the reaction mechanism will decide your next move. You always have a model of reaction mechanism in your head when you do reactions. For example, when you do the coupling, the last one, when we started that project, we did not know whether we are doing a CH bond activation or not. Okay? We were assuming it's a different type of mechanism. But then we do a lot of experiments. Finally, we came up with that. Actually, we can activate the sp2 CH bond. So the mechanism is always there. But today, I thought the audience are a bit different, not the all chemistry audience. So I changed my way of talking. Okay?
Only what is for the green project and the other
green chemistry, right? No, green right now, as I mentioned to you, is how many percentage is green. See? So when I say green, we started with always green in our head also, always green, green, green. But then the green is 10%, 20%. But the last one that we see is like 100% green. That means we don't even touch organic solvent. A plus B all end up to be the product, no byproduct, water, product crushed as a solid, we don't do extraction, no column product, filter. This is 100% green. But there are not many of these reactions. So we are trying to design the toolbox, as I mentioned earlier, the toolbox, many tools. So that when people do drug molecule right now, they can pick up on my toolbox and say that I use this one combined, I get this molecule. So we are trying to increase the tools inside the toolbox for this totally green one, totally 100% green reactions. Okay.
This is on the room temperature.
Yes, room temperature. We are not interested in reflux. Always room temperature. That is our ultimate goal. If the reaction doesn't go, that's the change project. Okay. And now usually sometimes we say, don't go reflux, okay? Don't go put in something else, put in until it goes. Sometimes the reaction, you start out with very beautiful reactions, it ends up to be very ugly. No matter, they end up to be 3 meters inside there. We also have this type of this.
Can we also do some reactions like they are inorganic, but they are not toxic, with water to give product? For example, we talked about titanium pentoxide plus water to give you titanium oxide and butanol.
Are you talking about solid catalyst?
Yes.
Okay, solid catalyst is another area we also work on that, but I don't have time. But that one we're collaborating with another one in China. Solid catalyst. We also do that. Okay. But the problem is that the solid catalysts are limited reactions, not that general. We are not interested in general type reaction. Like for example, you see our linkers are very general. It's only work with sulfur. Something like this. We like reactions that's very general. If your solid catalyst is very general, it can be used for many reactions. And also different substrates that we're interested. We don't want to have only one catalyst that only work with one substrate. Then it doesn't work with the other substrate. You know what I'm saying? So we also work on that. We are doing some sort of interesting reactions on the heterogeneous catalysis. Then after that, you filter the thing and then recycle it and reuse it. We have this type of thing also. You know.
So as you work on your biomolecules, so when you say water as a reaction medium, is it pure DI water, tap water, or some physiological solution medium?
Okay, so when you do water reactions, very be careful, right? Because when you do a glass flask, okay, with water, sometimes the silicate will catalyze the reactions. We know that also, we have seen this happening. So also, when we say water reaction, usually we have to change the vessel sometimes to plastics or Teflon. And make sure that you go, number one, okay? Sometimes the tap water is also dangerous. You have to repeat with distilled water and make sure it's safe, no problem. So the last reactions, we did all sorts of things. We've done all and found that. Now, we do it in water, but water is critical for our reactions. It actually is a promoter. No water, it doesn't react. So we have tried all sorts of different glass water, plastic water, all these things. Okay?
So no accidental metal contamination in the water?
Now, this is one thing that we have tried.
Regarding bio-inspired synthesis, so have you tried to add some like proteins or enzyme limits to
Okay, that would be
promote the
yeah. And when you put enzyme inside, okay, to do reactions, the isolation can be very complicated because enzyme cause problem inside the reactions. So a lot of times in the industry they use membrane separation. Okay, so we're separating this. We also try to do that. We have enzyme reaction plus water reaction in one pot manner. We publish this on paper. But the isolation of the product sometimes can be problematic with just enzyme reactions.
Okay, no more questions. So let us thank Professor Loh for.
Christmas present.
Thank you. Now, next month we will have another talk like this. It will be presented by Professor Atsushi Goto. He is the recent NRF investigator. So he will talk about polymer science.